Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Welcome to the debate. Today, we are dissecting one of the most expensive headaches in modern bioprocessing: the failure mechanisms of tangential flow filtration, or a TFF, specifically when you're processing complex fermentation broths.
And just to set the stakes here, we aren't talking about a filter needing a routine rinse. We're talking about catastrophic batch failures. You know, the kind where you are 40 hours into a campaign, you're holding millions of dollars of product, and then suddenly the flux collapses, pressure spikes, and you undergo a dynamic regime transition that turns your profit into hazardous waste.
The stakes are incredibly high. So the central question we are debating today is really one of predictability versus chaos. Is TFF failure a solved physics problem that we can manage through mechanistic models and digital twins? Or do scale-dependent chaotic factors like flow heterogeneity and the biological evolution of the broth itself render these engineering controls insufficient?
It's the classic battle, isn't it? The clean lines of a chemical engineering model versus the messy, evolving reality of biology at an industrial scale.
I'll be representing the mechanistic view. I believe that failure follows distinct, predictable stages. And if we use the right frameworks, specifically digital twins that can separate native from accumulated resistance, we can maintain control and accurately predict the point of no return before it happens.
And I'll be taking the complexity view. I argue that biological systems in large-scale hardware behave fundamentally differently than they do in a lab. Things like flow misdistribution, viscosity drift, and the fact that the broth is literally evolving while you pump it. Well, they create these false capacity illusions that standard models just miss.
Okay, let's get into the weeds then. I want to start by laying out the landscape of microfiltration, or MF. My core argument is that fouling isn't random bad luck. It is a structured process. When we look at clarifying a fermentation broth, failure evolves through three mechanistically distinct stages. The source material on glycerol fermentation broths is very clear about this.
Walk us through them. I have to say I'm skeptical about how distinct they really are in practice.
They are distinct if you know what to look for. Stage one is the rapid establishment of a surface layer. This happens fast, within the first 10 to 20 minutes of the run. You see a sharp drop in flux as the membrane initially meets the fluid, establishes a boundary. This is then followed by stage two, which is a cake-controlled quasi-steady operation. Here, the crossflow shear, the speed of the fluid sweeping across the membrane. It keeps the cake thickness in check. It's a dynamic balance.
And stage three?
Stage three is the drift toward irreversibility. This is where the cake begins to compress, or particles start jamming into the pores themselves. My argument is that if we monitor the rate of pressure rise, the DTMP/dt, rather than just the absolute pressure, we can get an early warning signal. We can actually predict the limit of recoverability.
I see why you structure it that way, but let me offer a different perspective. That quasi-steady state you mentioned in stage two, I think that's a dangerous illusion. In the real world, especially during long campaigns, you aren't just dealing with a uniform cake. You have a mixed foulant population, whole cells, cell debris, colloids, sticky extracellular polymers.
But physics is physics. The drag forces and lift forces don't change just because the soup is thicker.
The physics holds, sure, but the assumption of uniformity is what fails. The material notes that while you think you're in a steady state, the cleaning dynamics are changing under the surface. And this leads to my biggest issue with the mechanistic view: module hydrodynamics. When you scale up, you aren't just adding membrane area, you are stacking cassettes, and you get flow maldistribution.
You mean the flow isn't equal across all the channels?
Exactly. In a massive industrial stack, gravity and manifold design mean the bottom cassettes might get less cross-flow than the top ones. You create these weakest link phenomena. a local region fouls faster because of that pore distribution. Once that region blocks up, the flow is forced into the remaining clean channels, overloading them. It's a domino effect. You can't model that if your digital twin assumes the entire membrane surface is acting as one uniform sheet.
That is a fair critique of oversimplified models, but it doesn't invalidate the mechanism. It just means our twin needs to account for resistance fractions, which brings me to the distinction between MF and ultrafiltration, or UF. In UF, the failure mechanism shifts, fundamentally. It's not just a cake sitting on top, it's absorption and pore scale interactions.
Finally, we agree on something. UF is not just MF with smaller pores.
Right. In UF, we're dealing with proteins, DNA, polysaccharides. The failure is driven by interactions inside nanometer scale pores. The argument for control here is operating below a critical TMP. The goal is to minimize the irreversible fouling fraction by controlling the driving force. If we stay in that safe zone, we manage the life of the membrane effectively.
That's a compelling argument, but have you considered the gel layer? You talk about controlling TNP, but the material highlights that when you have retained macromolecules, concentration polarization forms a gel-like layer with strong osmotic contributions.
Which acts as a resistance, yes.
It acts as a wall. If you push the TMP higher, you aren't filtering faster. You are just compressing the gel. You get osmotic back pressure. So this idea that you have a safe zone is tricky because that zone is constantly shrinking as the gel compacts. You think you have control, but you're actually just densifying the barrier.
But that shrinkage is exactly what a digital twin can detect. A mechanistic twin separates native membrane resistance, let's call it RM, from accumulated resistance. It can attribute that accumulation to reversible versus irreversible components. The source material describes digital twin UF work that explicitly couples these resistance states to flux and pressure inputs. We aren't flying blind. We can see the gel forming in the data before it becomes critical.
We might not be blind, but we are certainly hallucinating capacity. Let's talk about the false capacity of scale-up. This is where the engineering ideal really crashes into reality. You run a feasibility study, you calculate your area-based scaling, and it looks great. But at industrial solids concentration factors, or CF, osmotic pressure and viscosity become dominant.
Viscosity is a parameter we can measure and input, though.
Is it? The material points out that temperature gradients from pumping create drift that looks like fouling but is actually a thermal viscosity effect. In a lab, you have small pumps. In a plant, you have massive rotary lobe pumps dumping kilowatts of heat into the fluid. Unless your model is correcting for the heat load of those massive industrial pumps, you are misinterpreting the data. You think the membrane is fouling, but really the fluid is just getting hotter or cooler in gradients across the loop.
That is an interesting point, though I frame it differently. That isn't a failure of the model, it's a failure of instrumentation. If we correct for temperature, the digital twin still holds. The core issue is separating the signal from the noise.
I come at it from a different way. The noise is the process. Take diafiltration, or DF. This is where time at risk becomes the killer.
Diafiltration is a standard unit operation. We can control it by choosing constant volume DF, where we sustain permeation, or constant flux DF. It's a solved control strategy.
But fermentation broths are not stationary fluids. They are alive, or at least biochemically active. The material mentions that during long DF processes, you have continued protease activity. You have aggregation. The broth evolves.
We know biology is dynamic, but how does that invalidate the filtration strategy?
Because as low molecular weight solutes wash out, the ionic strength drifts, the pH drifts. This changes the protein membrane interactions. You get absorption that wasn't there at the start. A model that assumes the feedstock is constant is going to fail because the chemistry of the feed is changing hour by hour.
I'm not convinced by that line of reasoning because it assumes we can't react. This is precisely why we need regime identification. This is where AI and advanced modeling come in. The twin isn't just fitting a curve, it's classifying the trajectory.
Classifying it as what?
As pore blocking dominant, cake controlled, or compaction dominant. The source material suggests that if the twin identifies reversible cake fouling, we increase crossflow. If it identifies adsorption or pore constriction, we reduce TMP or adjust chemistry. We match the mitigation to the mechanism.
That sounds beautiful in a slide deck, but the material also points out a massive gap: identifiability.
Meaning?
Meaning that multiple fouling mechanisms produce similar flux and TMP trajectories. A line going down on the graph could be pore blocking or could be cake compaction. Unless you perform perturbations like sudden flux steps, you can't mathematically distinguish them. And let's be honest, no plant manager wants you to start pulsing flux steps in the middle of a commercial GMP batch just to calibrate your model.
It's true that perturbations are rare in production, but we can look for signatures. For example, hysteresis influx TMP ramps, or the divergence between predicted and observed flux. If the model predicts a certain flux based on viscosity and pressure, and the actual flux is lower, that divergence is a signature of a changing foulant population, like the onset of lysis-derived fines.
Lysis-derived fines. That's a perfect example of the chaos I'm talking about. You are pumping this broth around, the shear from the pumps is lysing cells, you are creating fines that weren't there at the start. These fines shift the particle size distribution toward material that is perfectly sized to block pores.
Exactly. And that is a regime shift.
But it's a regime shift caused by the equipment itself, and the shear fields at industrial scale are different than in the lab. The material explicitly says that fouling parameters inferred in lab skids often fail to transfer because shear fields change. So your twin, trained on lab data, expects one thing, but the industrial pump is shredding cells and creating a totally different fouling scenario.
I see the gap you were pointing out. However, ignoring the mechanism doesn't help us. Even if the parameters change, the physics of filtration, Darcy's law, resistance in series, that remains true. The goal of the digital twin is to update the estimated parameters as the broth evolves. We acknowledge that Rn drifts with age. We acknowledge that resistance accumulates.
But can it update fast enough? And can it distinguish between a fouled membrane and a weakest link failure? Going back to the module hydrodynamics, if you have pore mixing in a large DF tank, you create local concentration pockets. The material calls these fouling nuclei.
Fouling nuclei?
Yes, a pocket of high concentration that compacts locally. Once that spot fouls, the flow redistributes to other areas, overloading them. It's a cascade. A global average model sees a gradual pressure rise, but the physical reality is a domino effect of local failures.
Which is why the mitigation strategies in the material include rebalancing parallel trains and redesigning manifolds. That is an engineering solution to a physical problem.
It is, but it proves that the solution often isn't better software, it's better hardware understanding.
I would argue they go hand in hand. You mentioned that cleaning dynamics scale poorly, that deposits which look reversible in the lab become irreversible in campaigns.
Right, chemical cross-linking, aging.
And this is where the DTMP-DT metric is vital again. If we see that rate accelerating, it's a sign of cake compressibility and aging. It tells us we need to stop now to clean, rather than pushing for another hour and ruining the membrane. That is actionable intelligence.
It is actionable, provided you trust the signal. But let's look at the false capacity again. The material mentions that area-based scaling predicts feasibility, but osmotic constraints cap the flux. If you are operating near that limit, your sensitivity to any perturbation, thermal, biological, mechanical, is massive.
That is why we operate with safety margins, and why the AI features must be physically meaningful. We avoid black box optimism by tying features to mechanisms. Flux recovery after a rinse tells us the proportion of reversible versus irreversible fouling.
In a postmortem, sure. But in real time?
The material suggests looking at the sensitivity of flux to cross-flow changes. That tells us if we are mass transfer limited or pore blockage limited. If increasing cross-flow doesn't help, we know we are jammed inside the pores.
Or it means the gel layer is so compressed that shear can't scour it off. I think we need to be very careful about assuming that increasing cross-flow is a free lunch. It increases energy use, it increases shear, it increases lysis, it feeds the feedback loop of failure.
There's always a trade-off, but the alternative is running based on raw data tags, just looking at a pressure gauge and guessing.
I'm not advocating for guessing. I'm advocating for humility, for recognizing that the broth evolves. The material says that long-term studies show a ratcheting loss of clean water recovery. That means every time you run a cycle, the membrane changes. It never fully resets.
I agree. The native resistance isn't a constant, it's a slowly drifting variable. A good model accounts for that.
And what about time at risk? We haven't fully unpacked that. If your filtration takes too long because your model was overly optimistic, the biology changes. You get aggregation. Now your feed stream is different. The model is predicting performance for the feed you had 6 hours ago, not the feed you have now.
That is the strongest argument for real-time updates. If we see the divergence between prediction and reality, that is the signal that the feed has changed.
So the failure of the model is the insight?
In a way, yes. The divergence is the diagnostic.
That's a clever way to frame it. But it still feels like we are chasing the tail of a very complex beast.
Perhaps. But let's look at the alternatives. If we don't use a mechanistic approach, we are left with empirical correlations that we know fail at scale.
Maldistribution will happen. We assume the broth will lyse.
We should design for that, yes. But we operate with the twin.
I suspect we are circling the central truth here, which is that neither approach works in isolation.
I think you're right. Let's try to summarize where we stand. From my perspective, the mechanistic view is the only path to scalability. We know that failure isn't random. It moves from rapid surface establishment to cake control to irreversible drift.
And I still worry that the map isn't the territory.
But by using digital twins to estimate those hidden states, specifically separating the native resistance from the reversible and irreversible fractions, we move beyond raw data. We can see the regime. We can see if we are blocking pores or building cakes. And frankly, the ability to monitor the rate of pressure rise, the DTM-PDT, gives us a predictive capability that human operators simply don't have.
I see the value in that, but I will maintain that the broth evolves. Models that treat the feed as a stationary fluid are doomed to fail in long campaigns. The failure at scale is often limited by hydrodynamics, mixing, shear, and flow maldistribution, rather than just the physics of filtration at a single pore.
So is it just chaos?
No, it's not random chaos, but it is dynamic regime transitions that are driven by the scale of the equipment as much as the biology. We have to recognize that what works in a lab skid might fail in a plant because the pump is different, the manifold is different, and the time at risk is longer.
That is a crucial distinction. The synthesis found in the source material really hits this home. Steady-state thinking is insufficient.
Absolutely. If you go in thinking you are going to find a steady state and stay there, you will lose the batch. You have to be ready for the shift.
The shift from early pore interactions to cake behavior to that dangerous compaction-driven irreversibility.
And recognizing that this shift might happen unevenly across the filter stack.
This has been a fascinating dive into the weeds of TFF. It's clear that while digital twins and AI offer a powerful flashlight, the biological dark matter, the lysis, the aggregation, the heterogeneity is still vast.
The best engineer is the one who watches the model but respects the microbe.
Well said. That wraps up this edition of The Debate. We hope this helps you navigate your next scale-up with a bit more insight into the hidden resistances waiting in your broth.
Keep your flux constant or maybe your volume. Just watch that pressure rise.
Until next time.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.